Okay, we're going to continue lecturing. We don't have too much to go in this chapter. And since it's on the exam next week, we're going to kind of wrap up the last little section of it. So again, if you need to move around to take a look at it, better go ahead. All right, so since we've been talking about gas laws, the next thing we're going to really talk about, and kind of the last thing we're going to talk about, is pretty much what occurred today in the experiment, which is partial pressures. And the idea of partial pressures, although it sounds really difficult, is pretty much this idea that if you have a container that basically only contains one gas molecule or one type of gas molecule, the total pressure of that container is all based on the pressure of pretty much gas A in this case. Now, oftentimes gases do come as mixtures of gases. So if you have a container that contains gas A and gas B and gas C, the difference here is they are each basically contributing to the overall pressure of the situation. So the total pressure of this situation would be the pressure of A plus the pressure of gas B plus the pressure of gas C. These are what are referred to as being partial pressures because they each contribute to the overall pressure partially. So they're a partial sort of component to the total pressure. The total pressure, like we did today in the experiment, if you were doing an experiment, would be obviously like the barometer reading. In a book type problem, you may have to calculate the total pressure or it may be given to you. So, how do we do this? Well, basically, probably the most common way that you could calculate a partial pressure is, frankly, just use the ideal gas law. So by just using the ideal gas law and again solving for P, which would be nRT over V, you can basically figure out the partial pressure of each gas in a mixture. Now, a couple of things which are really good when you're trying to do this is because they're all in the same container, they will all have the same volume. And because that container is in the same room on the same bench, they will all have really the same temperature. So if you were going to use sort of the ideal gas law for gas A, gas B, and gas say C in my example here, all the temperatures and volumes in each of those calculations will be exactly the same because they're all in the same container. And since R is a constant, it will be the same, obviously, for everybody. So really, when you're doing this type of calculation, the only difference is the moles of each gas. So a lot of times, all you have to calculate is the moles of each gas. And then, like I said, individually plug them into the ideal gas law and then add them together, and that would give you your total pressure. You could do this because, again, it's an ideal gas, like we talked about, I think, last time, that there is no interaction between different gas molecules. So even though there's multiple gas molecules in the same container, it's pretty much like they're in there by themselves. They're not going to interact with each other. So you can look at them as almost being in there by themselves. And that's why we could kind of do three separate calculations to do so. So here's an example of that again. In this container here, all the pressure is a result of the red gas molecules. Second container, all the pressure is a result of the green gas molecules. When we mix them together, they each contribute to the overall pressure, and their partial pressure of the red guys and the partial pressure of the green gas molecules will be added together. All right. We're not going to worry about this. So, no, we will. So again, like I said before, probably the most common way is just to use the ideal gas law for each gas separately and then add them together. You have two gases, do it twice. You got three, do it three times, four gases, however many you may have. So why don't we take a look at one? We have 5 grams of helium is added to 5 grams of neon, and it's in a 2.5 liter container at 27 degrees. What is the partial pressure of each gas, and what is the total pressure? So why don't you take a moment and see what you come up with. Helium is 4.003. Neon is 2018, I think. All right, so take a few moments. You should end up with 3 answers: the partial pressure of helium, the partial pressure of neon, and the total pressure. So again, a little ideal gas law for each one separately. So what we have going on in this situation is obviously we have a container here, and we got some helium guys floating around. We got some neon guys floating around. And what we know about this container is the volume is 2.5 liters and the temperature is 27 degrees Celsius. So as I mentioned before, probably the most common way to get partial pressures is just to use the ideal gas law. So if we think about the ideal gas law here, we have temperature, we have volume given to us, R, which is a constant, which we always have. So that's again a value we always have available to us. And we're looking for pressure here. So really the only thing that we're again kind of missing in this case to sort of solve for the partial pressure is the moles of each gas. And that again is typically the thing you're missing. So we just need to convert our grams that was given to us of each gas into moles. So we'll start with that. We'll take our 5 grams of helium. We'll use the molar mass of helium, which is 4.003 grams per mole. And that's going to give us our moles of helium, which in this case is, looks like we'll go 1.249 moles of helium. We'll do the same thing for our neon, which is 5 grams of the neon. And again, using the molar mass here, 2018 grams per mole. That's going to get us here 0.247, we'll call it 8 moles of neon. So now that we have the moles of each gas, we really have everything that we need to use the ideal gas law. But again, since it is still the ideal gas law, we want to make sure everybody's in the right units. So my volume's in liters, which is good. But like usual, my temperature is not so good. So we do need to add our 273.15 to that to convert us into Kelvin. And that's going to give us 300.15 Kelvin in this case. Now, we can use our ideal gas law, and we can just do it twice, basically. So I think I will move this upwards here. So my moles of helium was 1.249, and my moles of neon was 0.2478 moles here. So I'm just going to erase the bottom there so I can do a little bit higher. I know it's kind of hard to see some places in this room, so kind of go this way with it here. All right, so now that we got our moles of each one and we got everything that we need in the right units, we're just simply going to use the ideal gas law twice. So once for our helium, and that would equal nRT divided by V. So putting in my moles of helium, 1.249, my R, 0.08206 liters atmosphere Kelvin mole, my temperature, 300.15 Kelvin, all divided by my volume, which is the same, 2.50 liters. The moles will cancel, the Kelvin will cancel, the liters will cancel. That's going to leave us atmospheres, which is a pressure, so that's a good thing. And that will give us 1.249 times 0.08206 times 300.15 divided by 2.5. That's going to give us a 12.3 atmospheres. This number is the partial pressure of helium in this mixture. Any questions on that calculation? So basically just the ideal gas law. Now the good news is we're going to do it one more time, but we're going to do it for neon. And really the only thing that's going to change here is the moles. We want to make sure we use the moles of neon in this case. So we're going to go with 0.2478 moles. We'll still use obviously the same gas constant. We'll use the same temperature because they're in the same container. And we'll use the same volume because they're also in the same container. Once again, moles will cancel, Kelvin will cancel, liters will cancel, atmospheres will not cancel, even though I just put a line through it. And we'll end up again with atmospheres in this case. And we got 0.2478 times 0.08206 times our 300.15 and divided by 2.5. Going to give us a 2.44 atmospheres. This number would be the partial pressure of neon in this mixture. First off, any questions on that calculation there? So now we have the partial pressures of both gases in my mixture. To find my total pressure in this case, I am simply just going to add them together. So the pressure of helium plus the partial pressure of neon, which in this case, 12.3 atmospheres plus 2.44 atmospheres, going to get us something like 14.7 atmospheres as our total pressure. Obviously, if we had three gases, we would just keep continuing the same process and add them together. First off, any questions on that there? The major contributor to the pressure in this case is which gas? Which gas is causing the major pressure contribution? It is helium, right? It is a pressure of 12.3 versus a pressure of only 2 atmospheres. So helium is definitely the major contributor. Any ideas why that might be? The answer can be found right here with their molar masses. Helium is 4 grams per mole, neon is 20. Helium is much lighter of a gas. That means when it's flying around, it actually will be flying around a lot faster than the heavier neon. And because it's flying around a lot faster, it will cause more collisions and contribute to more pressure in that situation. So how fast a gas moves is related to its atomic molar mass. And the heavier the gas, it should be flying around slower. And the lighter the gas, it should be flying around faster at the same temperature. Any questions on any of that calculation there? Okay. We're going to skip this. We're not going to worry about that, I think. That's the one we just did. Now, another type of sort of partial pressure situation that can develop, not for you because they took this experiment out, which was the one we usually do next. But so this is an experiment we used to do next, which is, for example, in this case, they have some potassium chlorate here. And what they're going to do is heat it up. And what happens when you heat up potassium chlorate is it goes through a decomposition reaction and it will actually break apart. And it will break apart into little KCl and some oxygen gas. So as you start to heat this, and in this case, I guess I should balance it here. Let's see here, maybe a 3, a 2, and a 2. Let's see how I did there. 2, 6, 6. Sounds good. And when you start to heat this, what's going to happen is you're going to start to form this O2. And because the O2 has nowhere to go, it will follow the tube. And much like you did today, it will go into this bottle, this sort of collection bottle that was previously filled with water. And as the gas comes in, the water will come out. And just like today, you will be left with this sort of empty space within your collection bottle. It is really not empty. In this example here, it has the oxygen gas in it. Plus, it also has some water vapor in it. And H2O here is our water vapor. Now, the water vapor is only coming, much like it did in our experiment today, it is only coming because of how you collected the gas. It's sort of just a byproduct of collecting it with water. And this always happens in this situation. So if you ever collect a gas like you did today, or like in this example here, and water's involved where you're kind of displacing water, you will always get this mixture of gases. And this is also a partial pressure sort of situation. And the total pressure here will equal the partial pressure of oxygen plus the vapor pressure of water. Now, as we talked about and as you did in this experiment, the vapor pressure of water is a value that you typically look up in a table. So in your chapter there, you will have probably a vapor pressure table, and you may have to refer to it to look up some values if you're doing some problems like we did here in the class. We looked up there on the board on that table to find the vapor pressure of water. Now, the reason we want this is if we were doing this experiment, we are nowhere near interested at all about the water. We're really only interested about the oxygen because that's really the gas that we're trying to collect. So we're really interested about the oxygen. We're not all that interested about the water vapor, which is just really a side product. So we do have to do sort of a correction calculation like you did in your lab, where you can find the pressure of the oxygen would be the total pressure minus the vapor pressure of water. Now, if you weren't collecting oxygen, it would be really whatever gas you're collecting would equal basically the barometer reading or the total pressure minus the vapor pressure of water. And again, that's a very common correction that you do. How do you know you have to do sort of that type of correction? Usually in a textbook problem, they'll mention something like the gas was collected over water. So a lot of times they'll mention something like, hey, we collected this gas over water. Or very commonly, it will also sometimes just say your gas is saturated with water vapor. Those are like two key kind of terms that if you come across a problem, pretty much means it's just basically a subtraction problem for the most part. In most cases, you're just going to have to do this correction in this case. So let's take a look at one here. This, by the way, is a table from your book. The vapor pressure of water at different temperatures, and that is usually how you would look it up, is based on the temperature. Again, much like you did today, hopefully, you took the temperature of your gas and then you looked up the vapor pressure of water that corresponds to it. So if we have a sample of gas that is saturated with water vapor at 30 degrees, the total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the gas in atmospheres? Okay, so again, when I read this problem, that's the key sort of phrase there to tell us that we're kind of dealing with what we've been talking about, and that is this was saturated with water vapor. And that basically tells you have a partial pressure situation happening where, again, the total pressure will equal the partial pressure of the gas you're interested in plus that vapor pressure of water. In this case, you didn't have to look it up in the book or the table, but they gave it to you. Obviously, if they didn't give it to you, you would need to go look it up, and that's the vapor pressure of water, which in this case at 30 degrees is 31.824 torr. All total pressure here is 753 torr, and that means that we can basically solve for our pressure of our gas So in this case, our total pressure will equal the partial pressure of oxygen plus the partial pressure of the water vapor. That means the partial pressure of oxygen should be our total pressure minus the vapor pressure of water. And again, we're just going to subtract that to the other side in this particular case. So putting in our numbers, we'll take 753 torr, which is our total pressure, minus 31.824 torr. And we will end up with here 721 torr in this case. We do want atmospheres, so remember that 1 atmosphere is equal to 760 torr and 760 millimeters of mercury. So we'll take our 721 torr, we'll divide it by the 760 in this case to convert it into atmospheres. And that would get us here about 0.949, 0.949 atmospheres in this case. So the nice thing about these is it's really just subtraction in most cases, so not too bad in terms of the calculation. And again, those are the keywords you're looking for: saturated with water vapor, collected over water. You could also use this relationship, right? If you knew, for example, let's say you had something like this where, again, we had 3 different gases, and you know the total pressure is a result of each of those gases' partial pressures added together. And if you knew the total pressure and maybe you knew the pressures of A and B, you could also find the pressure of C by just subtraction, because the partial pressure of C would be our total pressure minus the partial pressure of A minus the partial pressure of B. So this is another sort of partial pressure type problem that you might come across, where you may be given the total pressure, maybe a couple of the partial pressures. You could also just subtract to figure out the partial pressure of the missing component. Again, this would be a situation where you would have all 3 of those gas molecules flying around in the same container, basically. A question on partial pressures here. All right, so to finish up this gas chapter, we talked about a lot of these sort of topics as we went through the different gas laws. But the kinetic molecular theory of gases, which you should know kind of the parts of it here, says that gases consist of tiny molecules. They could be atoms or molecules. The particles are so small compared to the distances between them. The volume of the actual sort of gas molecules are basically negligible and zero. And as I might have mentioned previously, this guy right here is one of the reasons that makes something an ideal gas, is this idea that the volume of the gas molecules themselves are much smaller than the container they're flying around in. And it's more important the volume of the container they're in rather than the volume of the gas molecules themselves. So an example of that, for example, would be if you took one of these trash cans and you put like a really small, like marble or something in it. The volume of the marble versus the volume of the entire trash can, the trash can is much more significant, its volume versus the volume of the little marble itself. So we don't have to worry about it in an ideal situation. Number 3 says that the particles are in constant motion, and as they collide with the walls of the container, these collisions are what exert our gases. So as we talked about, the more collisions that occur, the higher the pressure is going to be. The less collisions, the lower the pressure will be. Number 4 is the other component that makes something an ideal gas, and that is that the particles are assumed not to attract themselves to other gas molecules, nor will they be repelled by other gas molecules. And this is why what we just did with our partial pressures, we're able to do in an ideal situation, because even though we got all kinds of different gas molecules in the same container, in ideal situations, there is no attraction between those gas molecules. There is no repulsion between those gas molecules. Now, in real gases, which you'll learn about in 1A, are non-ideal gases, you actually do have to take into account those two things, number 2 and number 4. And that occurs, though, at really high pressures and really small sort of temperatures. Under normal pressures and temperatures, most gases will behave ideally. But if you get really high pressures, you will have super small volumes, which means that the volume of the gas molecule itself is going to be actually important compared to the container size. And also, with a slower temperature, things will be moving a lot slower, which means gas molecules will be near each other for a lot longer period of time, and they're bound to interact with each other. And under those conditions, those are what are known as real gases or non-ideal gases. The ideal gas law becomes a very scary looking equation known as a van der Waals equation, where you actually have to take into account how gases interact with each other, the volume of the gas itself. Good news is here we deal with only ideal gases, which you don't have to worry about that. So we don't have the scary version of the ideal gas law that you have to deal with. But when you take 1A, you will probably see that. Number 5, the kinetic energy of a gas is proportional to the temperature in Kelvin. So as we talked about, as you increase the temperature, you usually will expect your gas molecules to move faster. If you lower the temperature, they'll kind of slow down. And again, just to summarize some of the important relationships we talked about as we went through some of the different gas molecules. The higher the temperature, as we just talked about, faster moving gas molecules can result in more collisions and more pressure. As we slow down the temperature or lower the temperature, the gas molecules will be moving a lot slower and probably cause a little less collisions with the container. Pressure and temperature, if we have that rigid container like we have in Guy-Lussac's law, because the volume does not adjust, like we talked about, if we increase the temperature, we will see more collisions, and more collisions will increase the pressure, and we will see a rise in pressure. And again, that is what we saw with Guy-Lussac's temperature. And if we decrease the pressure, we will see a decrease in the temperature as well. Volume and temperature, which again is our Charles law relationship. Remember, it is the volume that adjusts to allow the pressure to remain constant by either giving the gas molecules more room to fly around in or give them less room to fly around in. The result of that is it keeps the number of collisions relatively constant, and that is how we keep our pressure constant. So as the temperature goes up, so does the volume. As the temperature goes down, so does the volume as well in that Charles law situation. And there it is. That is chapter 13.